which I discussed in the previous day. Even 2 hours I took just to explain that concept behind the testing of hypothesis. So whatever things which we come across up to this time, let me start with some. If you have any doubt regarding the testing of hypothesis, the procedure for testing of hypothesis, let me clarify that first. Then I'll move to the second test, because yesterday we studied only one test, one sample test for testing, or this one sample t test is used for testing the average of or specified average, or simply one sample. It's used for only specified average or for testing whether this correlation has a particular value or not. Mainly it is used for that population averages, purely one sample t-test. But while moving to two sample test or two sample independent t-test and paired t-test, I'll come to that. But before that, any doubt in yesterday's that concept, procedure, steps behind this? Okay, so let me share the screen. Okay, so is it visible?
Yes, yes.
Yes.
So yesterday actually we have seen this example. Okay, so the second one is two sample data. So it's very clear from that word itself. Two samples are there. Two sets of samples are there. Even I mentioned one example. Suppose we have the marks regarding marks from your class, part-time batch and full-time batch. So if we want to test whether the marks obtained by part-time batch and full-time batch across all over Kerala is same or not, or if whether there is any difference between the average marks. Okay, so this is used for testing independent samples. So that is a specialty here. Test for independent samples or test for equality of populations. Two sets of populations. Suppose we collect some data from this Kerala and some data from say Tamil Nadu. So to test whether the averages of these two states are equal or not. Based on average only, of course, based on average. Okay. So similar to this yesterday's expression. Sorry. So similar to this test statistic, actually here we use the test statistic. Of course, it's a lengthy equation, but only two terms we are using here: x bar 1 and x bar 2. Simply, x bar 1 is the average of first set of sample. X bar 2 is the average of second set. Then S1 square and S2 square are sample variances of two sets of samples. We have two sets of samples, then only it is possible to apply this test. Okay, so two sets of samples are given. It is possible to find the averages of these two sets. It is possible to find the sample variances of these two sets, which we denote it by S1 square and S2 square, and N1 and N2, of course, number of samples in each of these two sets. So, yeah, let me take one example. So the procedure remains same in both cases, not both cases, all tests. Whatever be the test which we are going to study, the procedure is same. That is, we start with null hypothesis and alternative. Set up the null and alternative hypothesis, choose the appropriate test and corresponding test statistic or test criteria. Then, while doing it manually, we will find the tabled value. Then, based on this calculated value and tabled value, we will write the conclusion, or we will decide either to accept or reject the hypothesis. But in software, we use p-value. So let us have a look at this example. A BPO company have developed a new method for better utilization of its resources, and 10 observations are. And one more thing, I don't know whether you all noted that why I choose small samples here. See here, actually I am going to take only 10 samples. Even in the previous example which I showed you yesterday, here also some I think some 30 only. So why I choose this small samples? One reason is, of course, while starting this topic, I started with a small data. But more than that, one more condition there. T-test is usually used if the sample size is small, say less than 30, less than or equal to 30. If for equal, for 30 samples, you can approach either t-test or normal test. So t-test is usually used, is applied, t-test can be applied only if the sample size is small. In statistics, usually we say small sample means 30, less than 30 is the small sample. So in the previous data, in the previous exercise also, I used only some nearly 30 samples, and today also I am going to use only 10 observations. But while moving to normal distribution, normal test, we will take the case of more than 30 samples. Okay. So 10 observations or utilization from both methods are given below. So here two methods are there. So 10 observations from each of these data is given. Check whether the mean utilization, mean, that average is specified. That's why we approach this test. That's why we are going to approach this small sample, because this is used for, even though it's known as test for independent samples, it is used to test for equality of averages. Population averages, that is understood, because we are applying this test for always population, but averages. So look at this null and alternative hypothesis to test H naught. So whatever we are going to test. So I mentioned it yesterday, we set up the null hypothesis that there is no difference. There is no difference means they are equal, right? So they are equal. Or this is same as this part is same as mu1 minus mu2 equal 0. That means mu1 and mu2 are averages of two sets of populations. See, by taking the difference means no difference. So that is why no effect or no difference. Then alternative hypothesis can be not equal to or greater than or less than, depends on your objective. Yeah. So check whether the mean utilization for both methods are same or not. And the data is given in utilization C.CSV. I'll show you the data set. See, only 10 observations are there. I have two columns. This is the first set of sample, and this is the second set of samples. But for this particular data, actually I have taken in both set of samples as 10 samples in both set, but it is not necessary that always we select the same number of samples in two sets. Maybe you can choose this, say, 10 samples here and 15 samples here, like that. That may or may not be different. So that is why we use in that criterion we use two terms, N1 and N2. N1 is the sample size for the first set, and N2 is the sample size for the second set. Okay. So let me open. Yeah, this is the one. So as before, it's of course this packages are similar to the previous one. First import pandas and this stats, then import this data set, utilization data set. So these two data sets I have showed you this. See, Just I called it by a name, say old and new. Okay. So this is the code. Stats.t test underscore IND. What is that IND? IND actually represent independent. So in the previous case, yesterday actually simply only one sample represents one sample. And here the difference is that we use this word IND. And one more thing, actually I mentioned we can choose the alternative hypothesis as less than or greater than or not equal to, or not equal to. Actually we use two-sided, two sides, right? Two tails. So by default we get the value equivalent to that alternative hypothesis as not equal to. But if you want to specify that alternative hypothesis or less than or greater than, you can include here as alternative equals less or alternative equals greater. That's your choice. So look at the output. So this is the output. This is similar to the yesterday, same thing. We are getting a t statistic. So we are getting this is our critical value or that calculated value, and this is the p value. So p value is 0.84. So how do we make the conclusion here? Yesterday I shared how do we make the conclusion? P value, based on p value. So if the p value is less than 0.05, that significance level alpha. So if the p value is less than 0.05, we reject the null hypothesis. But look at this p value, it is greater than 0.05. Since it is greater than 0.05, 0.84, of course, greater than 0.05. So we do not reject. We do not reject means we need to accept, right? So in this, for this particular problem, we accept the hypothesis that they are equal. They are equal means no difference. So we accept the hypothesis that those two things are equal. Averages of those two utilizations by two methods are equal. So that is why we reach the conclusion. Now, similar to this two sample independent test, one more test is there for that comes under this t-test, paired t-test. So I mentioned one example yesterday. Suppose I conduct a test before taking this lecture, so that I'll get a set of scores from you all. Okay. So before this lecture, one set of score. Then after this lecture, if I conduct that same test again, so that I'll get a set of scores, take those as after scores. So before and after. So I can check if I want to check whether this particular lecture is effective or not. So this paired data is there. That paired data is with me. So we can apply paired t-test there. Okay, whether that course is effective or not. So that's one real example. But the thing is that only one small difference is there in this. See here also some before and after data I can show you. Just a minute. Oh, sorry, I close this. Let me open in Adobe. Otherwise, Microsoft in between. Sometimes I'm facing some. Okay. Yeah. So this is the test statistic which we used in paired t-test. T equals, actually this also comes from the same formula, this one. Only thing is that in this case actually we have, in these two cases, in the case of independent sample t-test and in the case of paired t-test, we have two samples. So how do we coincide or how do we link those two samples? Let us take the difference between those values. Suppose I have one, say this in the previous example, say I have with me, say the score obtained by Sanish before this lecture as 40, after the lecture as 50. So just take the difference between the 40 minus 50 is UI. So similarly, I can compute the difference between those scores obtained by each of this in this group, right? So that is UI. Set of values are there. Find the average of those values, which is same as this U bar. Average of those differences. Okay, then SU is of course standard deviation of those values, of those differences, definitely these differences, right? N is the number of participants, right? So only slight difference in that formula. Then that's the remaining procedure is same. You can compute or you can select values from the tables of T distribution. But in the previous one, of course, here we used, I showed you one example with tables. Sorry. Yeah. Corresponding to n minus 1 degrees of freedom. Right? N minus 1 degrees of freedom. But here actually we use in independent sample test, we have two sets of samples. So we use the corresponding degrees of freedom as N1 plus N2 minus 2. So I explained that degrees of freedom yesterday. Degrees of freedom is simply number of independent observations, I can say simply that freedom we are giving. That word itself it is clear, or it is just a combination of how much data you have and how many parameters we need to estimate, or how much independent observations. How much independent, not observation, independent information, you can use the word in independent information goes into the parameter estimate. And one thing also to remember, this degrees of freedom defines the shape of T distribution. That's also another fact. I can say when this degrees of freedom decreases, that tail becomes more thicker. Those things are the features of that distribution. That's why yesterday I asked you whether you studied distributions or not. Because this is the only, I can say this is the only parameter, only unknown in that distribution. Just like mu and sigma in normal distribution, here we use only this n. And actually this property allows for what is the requirement of this, or what is the significance of this? This property allows for greater uncertainty associated with small samples sizes. Okay. So simply saying, this is the number of values that are free to vary, this degrees of freedom. Then a T distribution, then chi-square distribution, then one more F distribution. For these three distributions, actually always we define with this quantity, degrees of freedom. And one more thing, I will show you. Yesterday I just mentioned what is the relation between T, F, and you are not familiar with that. Let me, yeah, I have included one slide for that. Let me share what is the, simply saying, how do we connect normal distribution with this T? Then another distribution is F distribution, but look at this, F is capital letter, T is small letter. Use small letter itself. T distribution. Actually, that to us, it's completely saying students T distribution. Somewhere I noted that. Yeah, students T distribution. And this F also, that author, that statistician's name is Snedeker's F distribution. But usually we simply say a T distribution or T test, F test, like that. The third one is chi-square distribution. So all the tests which we are going to study, already we studied T distribution based on T distribution. Then we need to study one test based on F distribution, then one test based on chi-square distribution. But what is the relation between these distributions and normal distribution, our Gaussian distribution? Look at this. Yesterday I mentioned this. If x1, x2, etc., xn are n independent random variables following standard normal distribution, then x1 square plus x2 square plus etc. xn square follows chi-square. That is, x1 square plus x2 square plus etc. xn square means sum of squares of n independent standard normal random variables or standard normal distributions, standard normal variables follows chi-square distribution. Since we compute, since we take n samples, n random variables here, that's why n degrees of freedom. Okay, so that is the relation between chi-square and normal. Sum more squares of n independent standard normal variables. Then what do we mean by standard normal variable, standard normal distribution? normal distribution with mean 0 and variance 1. That is why n denotes normal distribution, 0 is the mean and 1 is the standard deviation or variance, because it's always positive. So the sum of squares of n independent, that condition is very important, independent standard normal random variables is chi-square. Similarly, what is the relation between normal distribution and t distribution? T-test we studied, same t. Okay. So if x follows normal distribution, actually yesterday I tried to explain this expression when someone asked me about that n minus 1. So if x follows standard normal distribution, that is x is a standard normal variate and y is a chi-square variate, then that simply we can say this the ratio of those two things, ratio. But just to normalize, we take here this denominator as y by n, right? X by square root of y by n, and one more condition, x and y are independent. If they are not independent, we cannot express this relation. Okay, so this is the relation between t distribution, normal distribution and chi-square. X is standard normal and y is chi-square. And one more thing, next one, f. What is the relation between f and normal? Straight away there is no relation, I can say, but this chi-square comes from normal. So f is simply the ratio of chi-square distribution. Ratio of chi-square. That is, if x and y are independent chi-square random variables, then x by n1. That here also I am taking using the degrees of freedom. So all, sorry, spelling mistake, it is. Whenever we define t, f and chi-square, define that those distribution with corresponding parameter degrees of freedom. Just equivalent to, I can say, normal distribution with parameters mu and sigma. Okay, so that is a case with the relation between. Now just go back to independent t-test. So I have showed you this one. Then we move to paired t-test. So I mentioned, let me take one example. So paired data. This is applicable to only for paired data. But in the previous example, that real example, that marks obtained by part-time and marks obtained by full-time, there is no relation between these two marks. So those two samples are independent. But here, of course, we need to take care of that paired data. Some relation between those two data. Okay, so 10 individuals have participated. Again, I choose only 10 samples because this is a small sample test. T-test, F-test, all those things comes under small sample. Small sample means less than 30. So 10 individuals have participated in a diet modification program to stimulate weight loss, and their weights before and after participating that program are given in a CSV file. So is the program successful? Right? So how do we assume the hypothesis? What will be the hypothesis here? Hypothesis means always we assume as no difference. So here also we assume the null hypothesis as there is no difference. There is no difference means that before and after are same. Okay, so we will set up the hypothesis like that, there is no difference. So let me show that. Pair t-test. See, after importing the same packages, import the data set before and after. So here actually one more column is there in that data set, subject. So just to remove that column, actually I use this idoc, right? So let me call those two before and after by B and A, before by B and B and A. Then simply look at this. The code is similar to the previous one, only difference is in this part. REL. What is that REL? In the first case, we used one sample. Second case, independent, IND. REL means related. That corresponds to related samples. We apply paired t-test only for related samples. So that is why in this code also that REL comes. Right? So same output. This is that statistic value. This is the p-value, and here a p-value is very high. Sorry, not very high. Here E minus 0.5. E means what is E? 2.4163 into 10 power minus 5. 10 power minus 5 means that decimal digits will come. Into 2.41 into 10 power minus 5. So 0.0000146 like that, which is very low, which is a very low value. Less than 0.05, less than 0.05 means we reject the null hypothesis that there is no difference. Right? Okay. So that is the case with t-test. So only 3 tests are there under this t-test. Okay. Now, the same case, that is the same 1 sample t-test and 2 sample t-test. 1 sample t-test is used for test for a specified average. 2 sample t-test is used for independent samples. So these 2 tests, if the sample size is large, say greater than 30, say 100 or 200 like that, the same test we use normal test, that is Z test. First one, test for population average. If the sample size is small, we apply t-test. In this test for population average, if the sample size is large, we use normal test. Similarly, here also, if we want to test for equality of population averages, if the sample size is small, say less than 30, we apply t-test. But if it is greater than 30, we proceed to normal test. Normal distribution, test based on normal distribution. But don't worry about the formula, the same formula which we use for central limit theorem, we use this normal, say x bar minus mu by sigma by root n. If sigma is population average is not given usually, we will replace it by sample standard deviation. Okay, so let us have a look at this question. A company claims that on an average it takes only 40 hours to process any purchase order. Based on this data, can you validate the claim? So what is the claim here? It claims that company claims that on an average, it takes only just for a comparison between the previous test. That is why I took this hours itself for as an example. 40 hours to process some order, some purchase order. So we need to test whether this claim, that is 40 hours, is valid or not. Right? So let me show you the data, PO processing data. See, simply that processing time is given. Simply that equivalent to that t-test example. Simply I took, but here one difference is that I took some more samples, say 100 samples. 100 samples are given. So 100 is a large sample. I can say it's a large. Not I am saying it's if n is greater than 30, definitely it comes under large samples. It's a large sample case. So it is greater than 100. So we use normal test. The procedure is same. Only difference is in that test statistic. Right. Now moving to normality test. Yeah. Here actually I used one more package, Matplotlib. I hope you are familiar with that. What is the use of this Matplotlib? Yesterday someone said, yeah, plotting. Yeah, I took one plot. That plotting is actually not a part of this normality test, but there is some I can say some significance or some importance to that. I will come to that. First, let me explain that test. It's similar to the same thing that t-test. So we use only these 2 packages for applying that testing, that normality test. So let me call by the name that PT. See? Yeah. Listen. So here, actually, that part is here. This one. Yeah. Here I use. See. One second. Yeah. This is the code.